So, welcome. My name is Demetris Zeinalipour, and I will be presenting this work on decaying telco big data with data postdiction and one photo, just to make it seem natural. So, this is joint work with Kostas and who is now at the University of Pittsburgh, Mohammed Mokbel, University of Minnesota, he also is at Qatar, and Andreas Konstantinidis, who is at Frederick and also working with us. So, and I think it kind of fits well to this picture of what we had today, like this whole IoT picture, lots of data ending up, in a data center. And the question is, what do we do? Do we push like data closer to the edges? Do we keep it in the data center itself? And do we start putting it, decaying it? So, I mean, this is, the motivation here is that, telecommunication companies, I should have actually taken this. The data inside telecommunication companies, like all other applications we saw today, started to explode. We have lots and lots of data. So what do we do by this? Let us just focus for a second to this very specific domain, the telco domain. Just to give you an understanding of what is going on in there, you have traditional data that is being used for all our data warehouses and analytics. Like every month you get a bill. This is basically generated from a database system, a traditional relational database system that generates a report with how much data you utilize. So the problem is that this is kind of small data, right? So it doesn't really give you the opportunity to exploit the biggest challenges. So for instance, churn prediction, which customers will leave the telco? Or how to optimize my 5G, my next generation network? Or how do the users, what is the experience of the users inside the telco? And then at some point, with all this advent of big data architectures, the telco said, okay, can we utilize some of this to acquire more data from the antennas, let's say? There's lots and lots of data that they haven't touched for many, many years. And this is when we start to talk about telco big data, because this is basically velocity data, data that is generated automatically at the cell towers and ending up in a data center, right? So we are talking about signal strength, call drops, counters, bandwidth measurements. So just to give you an understanding, this is about 5 terabytes per day for 10 million clientele. This is from Huawei actually, this number. So it's about 2 petabytes per year. And this is what gives us the 5 terabytes per day is, and the 2 petabytes per year is what makes this really big data. So the investments in this sphere are projected to grow. Actually, these slides are, already a little bit old, but many of the telcos have already invested in this kind of architectures because they want to unleash the real promises that are inside this kind of data. So, okay, of course, the first line of applications is to just use it for, let's say, marketing, customer acquisition, network planning, but there are many, many more applications that once you start having the data, you can think about new applications. And one of the applications we started to work on was actually traffic mapping, road traffic mapping in cities, right? Once you start collecting, all of this data in cities, you can actually have a better model of how the traffic behaves in the city itself. So, meanwhile, while working with this project and working in a telco environment for about a year with our students, we also kind of understood the challenges that are in there. One of them was this challenge of volume, right? The volume is growing, the data is growing, lots and lots of data, high costs. This costs a lot of money. At some point they were asking us if we could delete some of the data, right? Because they had enough big data, they wanted to get rid of it. So, and then, this is just an indicated number. A petabyte Hadoop cluster operating for a year with 250 nodes cost $1 million US. Whether this is $500,000, whether it's 250,000, doesn't really matter. It matters that it costs a lot of money And Herodotus also talked about optimization things to bring the cost down, actually, because it boils down to costs, like to dollars or euro. So, and then of course, once you have all this massive data, you also need a lot of time to process it. 1 terabyte of the data, 15 hours, a lot of time. So we have this general vision, and this is also the trajectory of our work, that we will have this velocity collection architecture that will allow us to skim data, extract the juice of it, provide insights into what is going on in a real telco environment, and then you can utilize this to do things like George said, giving back to the users and the community, how to exploit these insights, basically, like whether these are transportation agencies, municipalities. And so we started out with this architecture, and this was presented at ICD after working in a telco environment for a year. And then we also had this idea of mapping the network, the road traffic network out of this data. This was actually funded by IBE. Unfortunately, the telco was sold at that time, so we lost the project also. And then we identified this one problem of skimming data, how to decay data. And I will explain what data decaying is in just a few slides. And this got a Best of MDM award, and it was invited to Geoinformatica. Out of this, we also managed to create a tutorial on this subject of Telco Big Data, which was presented initially at MDM, and this year by Gostas in Macau at ICD 2019. And we also got a paper accepted in Geoinformatica that talks about the incremental aspects of the talk I will be presenting today, basically. So just to give you a little bit of a background, as I said, we also have a very extensive tutorial on this, but I'm not presenting the tutorial today, just presenting this one paper. So you have a telco that basically consists of what we call the radio network. These are the antennas, right? Where you have 2G antennas, you have 3G antennas, 4G antennas, and in the future maybe 5G antennas. And this is basically a hot topic now due to the advent of 5G, right? You hear about all these developments. The core network is all IP, I think since maybe 3G, right? So it's not too interesting anymore. It's all giga scale. Nothing interesting here. But after this, we have basically what we call the big data streams, right? Because these are streams from antennas, and we have two types of data: business supporting data. So this is gigabyte per day. This is the low scale data. And this is the big scale data, the terabytes per day, and this is what we call operating support system. These are the data from the antennas, and this is also from the antennas, but this is more like aggregates. For instance, maybe 80% of the 90% of the research in telco is doing research on the first type of data, because this is the easy data. It's inside relational databases, and they ask the telco to give them access to CDR records. CDR records, just to give you an insight, is I pick up my phone, make a phone call, it starts a session and it says, okay, you started this session here and it ended here. So it's more like a window. I might even have changed 3 antennas, it's still, just a session. So it's not really capturing, at a very fine granularity what I'm doing with my phone, right? But the NMS antenna, this type of data now is much more accurate, because it basically tells me the signal strength I get from the antenna I'm connected to, whether it's a macro cell or not, and it will tell me precisely this information. And so let's say here in this data you have a call quality. How good was your call? Do you have call drops? How good was your web surfing experience? In the PS data and the MR you have network measurements. I will tell you a little bit more about these network measurements. These are actually used also as a premise for geolocalization. I mean, telco localization techniques nowadays in the best case are 50 meters accuracy with training and their specific techniques. Just to give you an idea here, so you have the antenna here, you have a user, and the antenna now kind of measures the signal strength of the user that he receives on his smartphone. So the antenna has this measurement, the other antenna has another measurement, and then they have these aggregates. These are called counters, and the antennas themselves have these counters. How many call drops do I have? How many handovers do I have? And of course, you have also the signal strength, which kind of gives a record. I mean, at the conceptual level, you could maybe aggregate this and say, okay, I have this user that has this signal strength from these antennas, and then I could maybe localize the user if I want to. So, I mean, this is what we call really, the big data, the counters and these signal measurements. And at the conceptual level, we could create a nice entity relationship diagram that links together and consolidates basically, the different types of data you will find in an organization. So you have, let's say, cell towers that have basically a location that is known. Maybe you have, let's say, a network measurement data of a certain cell tower at a certain timestamp that gives you a certain counter for a certain type of thing. You have maybe the CDR data that I said previously. You might have all kinds of different data that are linked to each other. So we are talking about millions of rows, hundreds of attributes. You might have all these foreign keys giving you a complex, allowing you to answer complex queries if you want to. And you even have proprietary data formats here that require a little bit of effort to unlock. But once you have all of this, it's more like the internal data of a telco is like in a database schema. This is so okay. Assume that we have this massive data now in a nice relational database, which is not a relational database, but a data store, let's say. So how do we scale it down? Okay, we utilize data sampling. It's just sampling out randomly maybe some data. We're scaling the data down. It's a different thing. We do aggregates. It means that we have in mind a specific query, right? So we want to aggregate based on the sum, let's say, or the average, which is still bringing down the data. But if we have another query, we still cannot answer this, right? Because we didn't have this query up front. Then you have data reduction techniques. You talk to the data mining community. They have singular value decomposition, discrete Fourier transform. All of these are focusing on what we call the principal components. So it's just extracting the principal, the juice of the data again, which is bringing down data considerably, like being utilized in JPEG formats, right? You see the JPEGs are loaded in, from the most significant components to the least ones. Then you have the so-called statistics, data synopsis. Here we're talking about sketches, right? You have Bloom filters, histograms. All of these again are very coarse. You're bringing the data down considerably, but it's not like you retain you cannot recover, accurately the initial data. And then data compression is basically a combination of all these techniques together. So you take, let's say, gzip. Gzip is deflate on top of LZIP 77 plus Huffman, and Huffman is itself, based on, this counting of these Huffman trees and so forth. And the problem is that none of them considers the concept of decay. Decay for us really means that we will be fading out in time as time elapses. Like our memory. We remember precisely what happened yesterday, but maybe not 1 year ago. Maybe we remember a nice thing that happened 1 year ago, the birthday party that we enjoyed, maybe some time ago, but not everything. So this is like the premise of this work. So data decaying refers to the progressive loss of detail in information as data ages with time until it has completely disappeared. So there's a function of time here in this work, and the basic idea is to have full resolution of things that happen just immediately in the immediate past, and have less of less of memory for the older things. So you want to retain data exploration capabilities and save I/O. And there is also in the database community something called DB Schema DK, which refers to something else by Stonebreaker. It refers to the idea that the initial database schema will evolve over time because you have new operational requirements. So you have a different database schema over time. This is called DB Schema DK, but it's not relevant here. So what is data postdiction? Data postdiction is the opposite of data prediction. In data prediction, you predict something that will happen in the future. In data postdiction, you predict something that happened already. Okay, why do we do this? Because we already deleted what happened in the past. So that's the whole idea. You want to delete the big data that you acquired over time, and you just want to be able to do a backward prediction, predict back what you already deleted. So data prediction aims to predict something that will happen in the future. Data postdiction aims to predict something that happened in the past because you already deleted all of this, because you didn't have enough space. So this is like the idea here, the TBD operator. So we have a typical, here we have a typical telco big data architecture. It's acquiring data from the antennas. Then you basically start building, you have the snapshots that come in basically with some records. And each record here maps to a certain cell tower. And then in our approach, we also do some arrangement of cell towers into clusters so that we don't manage each cell tower on its own, but we rather manage them together in clusters. And then we create a model for each one of these clusters. And it will become clearer in a while. This is just the basic terminology I will be using. And the idea is, rather than building a monolithic model for the whole telco big data set we have, we rather want to build smaller models that will capture the specifics of certain cell towers, and that will give us better, predictive capabilities as we go and as the experiments show. So the research goal is to achieve decaying, as I said, and then we want to be able to recover as accurately as possible past things that we already deleted, and we basically need two objective metrics here. The first one is storage. How much storage do we actually need for the models and for retaining everything? And we also need the accuracy. I mean, of course, if we retain everything, we have perfect accuracy, right? But if we just keep the model and we ask the model in a while, it will give us an answer. How accurate is this answer? So we are measuring the difference of what the answer is from what the reality is, okay? And this is like the normalized root mean square error. Different ways to measure this. This is just one way for us to do so. So in our approach, we have a construction algorithm that does this. As the data comes in batches, we have here we take a chunk of it, of the old data. Like, we actually don't take the immediate past data because this is like now, and this is like the past data, immediate past, and this is like the older past. So we take this chunk here and say, okay, let us compact this. So abstract this into a model, and then store this model over here. And then you have the real data, some of the real data and some of the model. And then, of course, if you don't do it, you just have the real data, and you also have some space left, which will fill up in a while. And then if it comes to recovery, you will be using basically this and this and this together. And in this space, you won't be using any model, you will just be using the past log you have there. So here is the idea. You have all the cell towers, they generate data. Conceptually, we can organize them into clusters, okay? We could not have done this. It's actually quite possible. We could have done this per antenna, but here we do it in clusters because we want to do less model building computation. In our, experimentation, I don't remember, maybe it was something like 300 antennas, maybe more, maybe 1,000, how many? Well, it depends because every antenna has many sectors, so it's like ×3. So it's like one physical antenna is 2G, 3G, 4G plus.
I think it was 3,000.
3,000, okay. So I mean, but it depends on what you actually measure. So the monolithic model is still an option when not enough data, because you have the overfitting problem actually in this context. So here is a counter. In our case, from the schema I showed previously, it has a counter is an aggregate that tells you a certain thing for a certain antenna. For example, how many handovers failed, or how many call drops did I have on this antenna. And this is the big data that we mentioned previously. So here you have a certain cluster that has two antennas. It has all these different counters, and each counter has a value and it has a timestamp as well. So what we do initially is like we order the data. As I said previously, temporal and spatial dimensions become important here because we have lots and lots of data. So spatial organization we already achieved through the clustering. Temporal ordering we will achieve here. So the data is now temporally ordered. And then, and why? Because we want to be able to exploit the time domain, as I will present now in a while. So the goal now is to start learning, and learning at scale obviously brings in this scalable machine learning frameworks for big data, and in our case, I mean, the basic approach here is to use something off the shelf. We utilize LSTM. There is a reason for this, and I will explain this in a while, because it retains short memory links and long memory links. So the long memory links kind of remember the important old things. The short links remember the immediately past things. Even though, like, for the immediate past things, we also have the real actual data, and in the experiments I will talk also a little bit about that. But the idea is to utilize LSTM to actually exploit this as a black box. Okay, so so we create LSTM models for these partitions of spatial-temporal blocks, and then we want to organize this in a kind of data structure. So this brought up actually the whole theme of how do you do model management, because you might be using you might need to augment maybe these models at some point, right, to merge them, or in our case, we organize them in an ice tree. We start building an ice tree. In databases, we know how to build indexes, so we also built this index here. That is actually a spatial index that will bring you down, to the model. And once you have the model, you can fetch the model and ask it directly. And as I said, this could have been one model if you didn't have enough data. So, so just a primer also, for us and for others, in machine learning and neural networks. Of course, you have the initial, neural networks have been around for many, many years for classification, pattern and character recognition problems. And then, the recurrent neural networks are the ones that brought into the picture this idea of, forwarding state, between neurons, okay? And then you had basically the short memory, with RNNs. That was, okay, one thing. In the LSTM, you basically also have, other than the short memory links, you also have the long memory links. And that kind of gives you more capable, models that can give you, because they have these long-term dependencies, and that's why they are also very successful, in language modeling, auto-completion, machine translation, NLP, and they are also very popular in all these libraries, TensorFlow, Spark, and so forth. So, as I said, in the recovery step, we have this structure of models, and we can ask questions directly, okay, I'm basically interested to recover, let's say, last year's counter for the antenna in Limassol. Give me a value. Okay, that's basically the scenario here, and this is a query. And you want to be able to actually go down to the specific area, and then this encapsulates the time domain, right? This encapsulates the space domain. You go down to the model, you ask it, and it gives you the value. And the expectation is that this value is correct. And this is basically this is what we want to measure with the accuracy, right? And this is like the challenge, just to make this as accurate as possible. So let's see how this operated in experiments. I actually needed to say that we have also a demo at MDM, and we kind of put all these different papers under the sphere of the Telco Big Data Awareness Project that aims to create new awareness behind what is going on inside telcos. And but so we don't have time here just to show you, but this basically shows you that at the visual level, you can be playing the visual analytics over the raw data or over the compacted data, the data postdicted data, and not see a big difference, because the basic idea is still there. Because think about some decision support process, right? A manager doing decisions with his visual analytic interface, and he's basically seeing the result of terabytes of petabytes of data. And the thing is, okay, is it really so important to have pinpoint accuracy? Maybe, I mean, doing something within some error bounds is good enough. Even though we had a discussion about the error bounds before. So we evaluated this with a trace-driven experimental methodology. We had a real data set, but we explored here raw. Raw is just keeping all the data without decaying. Compression is just using a gzip library, using the SPADE architecture that initially only utilized compression with gzip. Sampling randomly, uniformly and randomly, and also the Telco Big Data idea with the two metrics that I presented earlier, the storage capacity and the NRMSE. And here you can see the data set. Yes, these are the cells from 2G, 3G LTE antennas, 100,000 million actually NMS records, 300,000 users, 10 gigabyte. That's the scale. It's not big data, but as I said many times also in my courses, we are doing big data ready research, not big data research, because big data, I mean, outside in the laboratory is sometimes usually difficult to find. And we have the KPIs, our calls, call drops, throughput, handover attempts, and these are out of all the 200 so many attributes that I said previously. We have a typical Telco Big Data processing stack with Hadoop file system, Spark for processing, Hive, even Apache Who that will give us, you know, a SQL-like interface that breaks down to Spark jobs. So you have SQL that breaks down to Spark jobs and does processing over the Hadoop data. And on top of that, we also have the Tensorflow that gives us the machine learning capabilities. And basically, we utilize LSTM, RNN, and GRQ. All of these are readily available there. And of course, going back to also Herodotus' discussion, it seems that this type of workload is being pushed down to the GPUs, right? So in the NVIDIA cards rather than within the cluster. I mean, this is just too intensive. The guys from Impact Tech are already doing it already on the GPUs. So, but nevertheless, here is a plot that shows basically on the left side the storage capacity and here the accuracy. Here we want to achieve smaller number. Here we want to achieve a high, smaller number as well, right? Smaller here means that we have good accuracy. We have less error actually. So, because this is error, this is an error metric. So here you see that for our approach, we retain 50% of the data because the model itself, as you can see here from the black line, is just, we retain half of the data, so we need 50% plus the model. And the raw approach requires to store everything, 100%. And then the question is, how good is this with respect to accuracy? So the answer is here that we have, I don't know, 40% error, okay? And on the other hand, of course, the raw doesn't have any error because you have everything, right? So, and this is just for one counter. If you come down to other counters, like the C counter, you are doing pretty well, even though you just kept 50% of the data. And I will be digging in more into this dimension of accuracy in a while. But just to compare it, obviously random is not a choice. You know what random means. We just have it there to make the plot look more expanded. And then the compression idea is actually, this one provides also optimal error because you retain basically everything, but at a lower cost. And CPU is not part of this plot. We could have accounted also for CPU just to see how much time it takes, but giving the cheap cards, and I mean the costs are probably going down because you have GPUs now, and Google even utilizes its own TPUs, right? So I mean that's the tensor processing units is a trend. I removed the slide actually because it's not so much related. So we had some control experiments here. We tweaked also a little bit the various algorithms. Neural networks, RNN. GRU is called gated recurrent unit. So it's very similar to LSTM, but okay, it's a technical difference. The GRU has 2 gates, reset and update gates, where LSTM has 3 gates, input, output, and forget gates. And once you look at the gate diagrams, it's probably easier to understand what the differences of these are. And machine learning experts are also the one that would be, redesigning this into more meaningful, into new approaches, right? This is their job. See, it's not even here. So, nevertheless, what we see here is that the percentage doesn't drop, of course, because we still keep 50% of the data plus here, the model itself. But the accuracy is best for LSTM because here the error is very high. It goes a little bit less for GRU, and for LSTM, it's actually not bad. And this all has to do with specific counters. And this also kind of brings up the next question. What are the error bounds for these errors? Is there any way to do this upfront before I start out? And we are actually working on a follow-up idea that will generalize this operator beyond Telco Big Data into any type of data with these types of error bounds, plus make this work even for maybe text data and numeric data and spatial temporal data. All of this has to be investigated to make this a complete work. But this already looks very promising. And actually, let me tell you this, that we have the IoT data nowadays generated. It's being, over the years, it was transferred to the cloud. We saw lots of works about how to optimize processing in the cloud. Now there is a discussion to bring down the computation again to the edges, George, for example, or even new actor models to process the data once it's in the cloud. So our approach sits in the cloud. It says that, okay, data will still be in the cloud, but it will be reduced. Its size will be reduced because also data vendors cannot keep it forever, but they still want to retain the most important things of what has happened in the past. So it's still a question of what will happen in the end, whether data will be edgified or not. So until it's clear, we will explore both ends. And my kind of intuition is that once we started to have a global image of things in the cloud, we don't want to lose access to this big picture, because anytime you can log in, see every single measurement that has been acquired in the cloud, why would you want to lose this for some distributed edge architecture where you don't actually know where the data is? Where it's out of sync to, and network capacity is increasing, right? We have 5G networks now. This is the whole idea that you will have millisecond access to the terminals. And you have, all of this makes us a little bit skeptical of where things are going. But for us, space and times are important dimensions, and this has been understood through this talk as well. So we want to generalize the DP operator for many different types of data. Improving the computational time is important, but on the other hand, we also see the processing costs going down, because we see a shift from these big data architectures into the GPUs and the TPUs when they arrive. And we also want to provide extension to allow, we already actually worked on this, and this is actually part of the Geoinformatica paper, where we try to, this is another problem, how to augment models as you move on with time, right? What are you going to do? We do it in a pretty simple way, but I think there's more space to augment these models with new data. So, thank you very much. Is there any question? No? George?
How do you choose the optimal window for decaying data?
So, you mean space, time window?
No, when you run the model. I mean, how do you choose how many data will you use for training the models and how much data you will decay?
So, as you probably saw through the experiment, this is all very static now. Okay, we have actually one more control experiment where we played with 25%, 50%, 75% decay. Just to, I mean, in control experiments, you usually find, you know, just by example, the best point, but there isn't any general approach to find it. I mean, you know, at least in this work. But I think it's interesting, I think, to note it down as, because as I said, we are working on this as a generalized. This is probably going to be a point that...
I think that this is a user-defined factor. I mean, if you want to delete the one last year data, you do that. So you decay the last year data.
Well, it's a factor of accuracy though, right? If I know I can delete 1 year worth of data and only lose 2% of accuracy versus...
So stop to the simulations.
It's again the cost, because what is the cost of training? 1 year of data, what is the cost of training only 6 months or 3 months?
Yeah, I mean, this whole streaming idea is something that we have, because now we are buying new hardware, as I told you, GPUs, and so we will be looking more at the operators provided on the cards, because I think, as you mentioned, is that they have ways to combine models, right? So, I mean, if there are processor-ready methods to do so, then you have to exploit those. If you don't exploit them, it's like doing everything in a high level and efficient way that will cost a lot of money. But we want to look at this problem from the perspective also of new hardware, which is important. Yes?
Okay, so I was a little surprised that compression in your experiments did quite well, in a sense. Okay. So
For this one?
I think it was one of these. Yeah, so
So here the error.
Yeah, the missing line is
the missing line, I mean, because compression is zero error, but you know, actually it's just a little bit above 50% of the data scattered.
So yeah, I mean,
So-
if you compress 70% compression is actually expectable. I mean, if you compress any file with gzip, it's probably 40%, the best case. Like try gzip on any file, it's going to give you 40% compression. But here, okay, here it's something like 60%. Okay.
So the question is more like, so it seems that there is some space there, because you could combine like compression with your technique, right? And then maybe get
At
like,
the end, yes. Yeah,
because they seem to be composable in some sense. Right?
Yes, but the thing is that the model actually costs nothing. Like the model, as you see here, is just one minor data file, and then where we spend 50% of is actually the real raw data, but we decided to keep as a 50%. And actually, this is a plot here that shows what I explained before. That you have, of course, the option to say decay 25%, 50%, 75, or even 100%. You have this choice, and if you decide to do 100%, the storage cost goes down to nothing, just the model. But then, this is a problem. If you ask the user, if you ask any company, they want to see what happened yesterday, what happened last week, what happened the previous month, maybe previous year. They say, okay, maybe the model is good enough for us. That's the whole point, that you want to do analytics in the past, visual analytics for the time being.
But it's but what I mean with compression is essentially like if you could have different compression techniques, you could
Yeah, in the ICND 2017, we compared all compression techniques, and we identified gzip as the best one because gzip has the best. This is in the ICND 2017 paper. The reason is that gzip is also has this benefit of being directly compatible with the Hadoop ecosystem, so it can be applied on the socket level directly because you have gzip sockets. And then in the I/O, the network I/O is directly compressed, right? So it's also a compatibility issue at the end of the day. Yes.
When you have a huge amount of models, is it possible to delete some of them and create new models based on the deleted?
Yeah, I mean this whole idea of managing models is something that we don't have very solid answers for the time being. But okay, the way this works currently is that the models don't cost anything, so we keep all of them. And I think this whole discussion around models will emerge in the future because you also look at GDPR, for instance, they say, okay, you have to delete the data. What will happen with the model? Does the company retain it forever? They don't say anything, right? So I mean, this whole sphere of model data management is on its own right, very interesting for research. But no, at the time being, we just keep all of the models.
So I wanted to ask you, I'm not familiar with the Telco Big Data nature or values or so, but what do you do with anomalies? Because there are certain fields where anomalies are valuable, and if I'm familiar with LSTM or this kind of networks, if you delete those values, the postdiction will not bring those anomalies back.
Right. So I mean that's the whole thing now. That if you are the telco operator, you have full resolution to what happened yesterday, 1 year ago, even now. So you have all this triggering system that will send you SMS. The network is down, or the model of what the network is supposed to be with what actually happens in the network doesn't match because that was one of the applications. But then, if you, if it already happened, it's probably less important. It's just important for research purposes, for them just to, after a year what happened, it's probably just important to be able to go back and see, okay, what happened last year when we had the final of Apoel versus Apollo? What happened? Was the capacity enough? And then, at that point, you want to be able to maybe, for last year, you probably have the real data, but maybe for 5 years ago, you just have statistics. So you can go back and utilize those models too. And if it was an important event, if it was a spike, this is actually the whole essence of LSTM, that it will extract those important events. That's the whole thing with deep learning, that you feed it with enough data, and it picks up the thing that deviate from other things in a way that they are important events. These are latent. It identifies the latent dimensions of the data. You don't know what the important things are. This is what identifies the latent dimensions. Yes, thank you.